All right, this is the pre-lab lecture for our recrystallization experiment. And this week we will be purifying acetonilide through the process of recrystallization. So to summarize, ultimately what we're doing this week, we have to first determine the best solvent for acetonilide recrystallization. You'll be recrystallizing and decolorizing your acetonilide to remove any impurities that might be present. Ultimately, once you have recovered the purified acetonilide, you'll be taking melting points of both the crude and purified acetonilide to compare those numbers to one another and to serve hopefully as proof that you successfully recrystallized and purified your acetonilide. Don't forget, this is a full lab report experiment. I'll make another video emphasizing what things you need to put into your lab report later in the week, but be sure to take really good notes for this particular experiment and record all of your data. Just as a reminder, future labs will not describe in detail how to do a recrystallization. They'll just say recrystallize the product and expect you to know what that means. So pay careful attention to what you're doing this lab and make sure that you are able to conduct a recrystallization from here on out. A little bit of background. As I've mentioned, recrystallization is a purification process. It removes the impurities from compounds that are soluble at room temperature. It's based upon the idea of solubility and the fact that a compound, that the solubility of a compound in a solvent increases with an increase in temperature, and that the converse is also true, i.e. that as a solution cools, compound solubility decreases, meaning that this allows for crystals to form as the solution cools or crash out, as the phrase may be. As your solution cools and crystals are formed, they form in a very organized manner, and we see here in figure 1 kind of that illustration of individual molecules kind of laying down, and if they are in a pure solution, or if pure crystals are what's laying down, they lay down in a very organized manner called the crystal lattice, which you probably talked a little bit about in general chemistry. Impurities don't allow for the crystal lattice to form as neatly, and so your impure crystals usually don't look the same as what your pure crystals do. There's usually some types of differences in their visual appearance. So the most important part of a recrystallization is choosing the right recrystallization solvent, and that's the first thing you'll be doing in this week's lab. So for our particular technique, what we are wanting to do is to find a solvent that your impurities are very soluble in, but your material, i.e. for us, the acetonilide, is only soluble in at high temperatures. That's because as the solution cools, we want our impurities to stay liquid so that they can be filtered off, but our acetonilide to crash back out or crystallize out once the solution has cooled so that we can recover crystals. So remember, the boiling point of your solvent should be lower than the melting point of the product you're purifying. You can look all of this information up. Not only that, but it's probably in your lab book. Certainly you can find it online. If the boiling point of your solvent is not lower than the melting point of your product, then something called oiling out occurs. And what that means is that your product is deposited as an oil, not as a crystal, because the compound is insoluble in a solution at a temperature above that compound's melting point. Figure 2 is a figure from the book. To me, the most useful illustration here is line A, showing that as your material, as your solution gets increases in temperature, then your solubility increases as well of that material. Of course, line C and line B are also showing different ways that impurities can potentially impact the solubility of a material. Things to keep in mind as you're doing a recrystallization. There are things that you've learned for a long time now. Remember, like dissolves like. When you're estimating which potential recrystallizing solvent you will you might use, look at your material and the structure of that compound and identify solvents that share those intermolecular forces. Traditionally, when you are deciding on a recrystallization solvent, you're testing several solvents and comparing them to one another. You're not just trying one and then moving on and trying another one. You usually test several at once, which is what we'll do this week. The other thing to remember, you need to be able to produce a lot of crystals, so you don't want to use too much solvent. Table 1 in your lab book is a list of commonly used recrystallization solvents, and they happen to have listed them in order of decreasing polarity. All of these you should be able to look up and determine what their structures are, with the exception of petroleum ether that's actually a mixture of hydrocarbons. So there isn't a specific structure for what that looks like. Table 2 in your book is kind of a list of requirements for selecting your recrystallization solvent. Remember, the compound being purified has to be insoluble in the solvent at room temperature. The compound must be must be soluble in the boiling solvent. The solvent's boiling point must be lower than the compound's melting point, and an abundant quantity of crystals must be recoverable. All the things that we had just highlighted, but succinctly put in a nice table in your lab book. For future reference, there's a second way of creating or determining a solvent for recrystallization, and that's called using a solvent pair. I'm going to talk you through that very briefly in case we need to use that again. For starters, in a solvent pair, you're using two solvents, and the two solvents must be miscible, i.e. mix thoroughly and basically dissolve one another. So you don't want any solvents that would create layers with one another. Basically, when you're doing these kind of solvent pair recrystallizations, it takes advantages of the properties of both solvents. So there's definitely some pros to using this technique. First, when you're trying to create a solvent pair, first you dissolve the crystals in a minimum of boiling solvent, your first solvent, whatever that may be, and then you add just a little bit of your second solvent, drop by drop with a pipette, to the boiling mixture until it becomes cloudy and you're precipitating out your product. You just want to bring it out of solution, and then after you see the solution becoming cloudy, you add a few drops of the first solvent to redissolve the precipitate. From there on out, the solvent pair is treated as effectively one solvent, and you move on through the recrystallization process the way that we will describe it going forward.